Morning, everyone. Thanks, Brian. I wanted to tell you a little story this morning about a project that several of us here in this room worked on over the last 2 years regarding photometry on Hubble's first Cepheid variable in the Andromeda galaxy. I guess I got to point it at it. So the first little quiz, how many of you remember this slide, which Arnie Hendon presented to us all in 2010, you may remember. And he pointed out that the AVSO had been invited to take on a project of determining the period and the phase of Hubble's Cepheid in the Andromeda galaxy, and that it was going to be used by the HST for imaging by the Hubble Heritage Project. Now, the Hubble Heritage Project, as it turns out, is the public outreach arm of the Space Telescope Science Institute, and they had an interest in trying to promote this as one of Hubble's first targets. And it's also a historical target. I hope to talk about that a little bit today. Cepheids were pretty well known 90 to 100 years ago by their light curves, but there wasn't really too much known about them until Henrietta Leavitt, working at the Harvard College Observatory, started working on them. She had been following hundreds of variables in the Large Magellanic Cloud, and amongst the Cepheids, she noticed that the brighter ones had a longer period. And since they were all at about the same distance, everyone realized, wow, if I can measure the period, I'll know something about what their absolute luminosity was. But calibrating this period to luminosity scale turned out to be a real problem because, again, 90 to 100 years ago, the most standard way of measuring distance was parallax, and there are hardly no Cepheids close enough to Earth to measure with parallax means. As it turns out, Harlow Shapley at the time had been measuring the distances to galactic clusters using giant stars. And so Shapley came up with the first calibration, because in these galactic clusters, some Cepheids were known, and so Shapley took those distances he had measured and applied it to this Cepheid problem and came up with the first calibration. And it was the calibration that Hubble later used. The other big thing that we have to remember about 100 years ago is that spiral nebula were not well understood. Were they a part of the Milky Way? Harlow Shapley had argued that they were, that the Milky Way was an island universe and all these little things were a part of the Milky Way, whereas we also know that Newton had said that space was infinite, eternal, and unchanging, two of which we know now are not true. But even the philosopher Kant had said, you know, the farther away things get, the smaller they're going to get, and they're going to be unresolvable. So, of course, they're at great distance. And, of course, small and unresolvable reminds you of the common modern term, faint fuzzies, which we all know them as now. But this was the plate that changed it all. In 1923, this is a scan of Hubble's 4x5 plate off the Hooker telescope in 1923, and you'll notice that there are three objects marked with N, which for him meant nova, and then in the upper corner, one of them is struck out, and it's marked VAR with a big exclamation point on it. And you'll also notice that on the opposite side of the plate at the very top, it's logged in as being H335, M31, 45 minutes, and it's marked October the 5th, 1923. This is actually a scan of Hubble's log of the time, and it's a columnar format. On the left side, he's got plate number, an object, an RA index, and there's also a column for quality. And on the right-hand side are remarks, where he's written in things about that particular plate. And if we look at the left side a little more carefully, we see that down at the bottom, this is a 2-night run at Mount Wilson from October 4th and 5th. And here at plate 331, I note that he's observed M31, but the plate's quality is marked as being very poor. And down here the following night, at plate 335, which is the one I showed you just a minute ago, the plate quality is marked as good. In fact, it's the only plate in that whole 2-night run that's marked as good. All the rest of them are marked as poor or fair. So even with the largest telescope in the world at 5,000 feet, you're still subject to crummy skies. If we go over to the right-hand side, this is the remarks side. On 331, we note that he's marked nova suspected. This was on that poor quality plate. And down here at 335, it says confirms nova suspected. And he's also written in a comment. And you can notice that the comment was written in at a different time. It's in a lighter pencil. So he probably went back to his log at a later time to write this in. And it's got a big bold arrow on the right-hand side pointing out the comment. And the comment says that on this plate, H335, 3 stars were found, 2 of which were novae, and 1 proved to be a variable later identified as a Cepheid, dash, the first to be recognized in M31. So when you look at that comment and this big bold arrow, you can just feel the excitement that Hubble must have felt. He had found a Cepheid variable in one of these spiral nebulae. This was going to be a game changer, and he knew it. Later, he found 12 Cepheids in M31, and in 1925, as he was preparing to write this up for publication, he wrote a letter to Shapley describing his findings and all about the Cepheids in the M31. And Shapley is known to hold up the letter and say, "Here's the letter that destroyed my universe." Later, in the 40s, 20 years later, it was discovered that there was actually 2 classes of Cepheids. The ones they've been looking at in clusters were actually old type 2 stars, very small. And the classic Cepheids, the disk Cepheids, were type 1 stars, much larger, 1.5 to 2 magnitudes brighter, which meant that all these measurements out to Andromeda and the other close galaxies were way off. They were much farther away than they thought. And practically overnight, the universe doubled again. Cepheids are still important today. In fact, one of the original justifications to even build a space telescope was because of Cepheids. One of the projects was to image individual Cepheids in galaxies up to 100 million light years out, which for me is just staggering to even imagine. 2010, this is where the AVSO project began. An alert notice went out to the members on that list. A VSP chart was published, and here it is with the sequence. This is one of my images of the field, and I came to look for these 2 little field stars because they kind of point to a triangle down here in the muck. You can barely see, but the triangle, contains the Cepheids that we're looking for. I think it's interesting to remember that just about every star image you see on this image is actually a foreground star in the Milky Way and not really a part of Andromeda. This is a pretty interesting contrast. This was done for me by Martin Burkhead, who is a professor at University of Indiana. He took my image with my little field stars and my triangle, and he scanned onto it the image taken out of Hubble's 1925 paper. And it shows, Hubble shows the object at minimum, whereas my plate shows it at maximum. So this is a pretty interesting comparison and contrast, I think. So during the 2010 season, about 200 observations were made on this target, most of them in R, some of them in V. The target's about a half a magnitude fainter in V, so it's well down into the 19s at minimum. Matt Templeton, the science director, AVSO, published a real nice paper, very detailed about the history of the target and about the analysis of the data that the AVSO had accumulated. And Hubble Heritage got what they wanted. They wanted an ephemeris, so here was the ephemeris that Matt published. It showed a JD start, it showed the period, so they could go out and calculate the maximums and the minimums when they wanted to do their imaging. Martin Burkhead also compiled this for me. It shows Hubble's light curve from his 1925 paper. And interestingly, Walter Baade had studied the object extensively in the 1950s with the 48-inch and the 200-inch on Mount Palomar. The data was published by Swope in 1965. And you can see that they came up with a period of 31.38. We're going to see that number again. And on the bottom, Martin's included the AVSO light curve. And I think everyone can be proud of the light curve that came out of the work. Here's the HST image of the field. And I looked at this thing and I thought, oh my goodness, where are my field stars? You know, where are my triangle? It's got to be there somewhere. Well, it took a while, but I discovered that down here in the left corner, there's my triangle. And over here, that's the variable. If you look at this on the website, they've got an animated GIF, and you can actually see it go from maximum to minimum. And as I said, Hubble Heritage got what they wanted. They put up a real nice chapter on their website, The Star That Changed the Universe. I think I've shown that it did that. And they published this light curve. This is a nice smooth light curve, and all those red dots on the left-hand side are all the AVSO data points that went into the targeting, and the bold stars on the right-hand side are the times when the Hubble was actually used to capture the images that generated that image I showed you a moment ago. So that brought the 2010 project to completion. However, Matt Templeton, encouraged a couple of us, or some of us, to go ahead and continue to work the project for another year, because Matt's theory was the longer time span we had, we could actually reduce the error on our measurement if we went ahead and did another season. And Matt speculated that we could reduce the error to about a third. So anyway, the second year's challenge was to work on reducing the error. We went ahead and continued the imaging, and I downloaded all the 2010 data as a batch and then separated it out by observer. One of the problems Matt had that I had to solve also was zero pointing all the various observers to one another, because everybody's system's a little bit different, and you want to get them all as close to possible as you can. So I did this, and I also felt like I had to be in agreement with what Matt had found. So anyway, this is what all the observers for 2010 look like in Paranzo. I brought them in one at a time, and Paranzo's got a bunch of tools to move one observer up and down a little bit, compare it on the phase diagram so it looks like it's smoothed out. There's also a binning tool, which is very handy for comparing one observation to another. So this is what the 2010 data looked like after I got done with it. And we always hear the story, should I observe tonight? Is it a bother? Will it count? Well, I hope you've noticed that right up here in the corner is one observation by Gary Walker. He's here in the room. He was the only one that caught this maximum. And I can tell you, while running Paranzo, adding Gary's observations to the system did improve the period and it did improve the error, just by catching one additional maximum. So if you're ever in doubt, get out and do what you got to do. This is what the 2011 data looked like. There weren't near as many observations, and the data looks a little bit less symmetrical, but it is what it is. And this is what the combined 2010-2011 data looked like. And when I got done with this, Matt and I had quite a discussion about error and about calculating error. And he had come up with some references in his paper that I felt I needed to pay attention to. So I went back and did some reading. Turns out one of the authors Matt referred to, Lensenberger, had actually produced a program for analysis of astronomical data using a Fourier transform. And it produced some of the numbers that Matt had used. So I thought, okay, I'm going to shift gears and I'm going to see if I can fit in with what Matt had done here. So I exported all the data out of 2010 and 2011 separately, now that it had all been zero pointed, and brought it into this program called Period 04, which is available online. It runs in a Java environment, so it'll run on anything. And presto, the numbers looked really good. Here was 31.38 again, and the error was plus or minus 0.09, and if you use your high school math rounding numbers, it rounds up to 31.4 and 0.1, which was just what Matt had found. So my confidence level went way up. You know, I was on track. My zero pointing had worked. I got a number that was like Matt's. So I was confident that it had been successful. So then I went ahead and brought both years in to period 04. And period 04 it does it iteratively. You can keep hitting it to reduce the residuals. So you don't get a nice smooth curve because it keeps adjusting as it goes along. And so presto, the number did reduce by a third, just like Matt had thought it would. The error is now reduced by having a longer span. But I'm sure you've all noticed that now the period is reported as being on the big side of 31.4 instead of being on the small side of 31.4. So while I can say that we're sort of in agreement with what's been done before, I think it's also worth noticing that comparing what was happened 60 years ago by Bada and 90 years ago by Hubble, this star may have changed its period. The period may have grown and become longer. And I think our data now sort of supports that. So anyway, this wouldn't have been possible without the observers. There's a bunch of people in the room here that were participated in this. Yours truly. And then Steve Smith, who is here, although I haven't met him yet. There he is. Yay, Steve. He's from Sonoma. Also Arnie, of course. Arnie was one of the initial observers in the first year, and he also provided our comp star sequence for us, a big part of it. Then we also have Richard Sabo, who is from Montana. Richard's in the back. Thanks, Richard. And we have, get to my next page here. Gary Walker from Massachusetts. Gary's the one that caught our one maximum. And Robert Buckheim, a regular here with our SAS operation. Different tie, okay, yeah, I'll go for that. Tim Crawford from Oregon. Tim could not be here, although he was a contributor both years. And Michael Cook, who I understand here. Oh, there's Michael. Okay, Michael's here today also. So thanks, Michael. And there was a few other observers that I don't have pictures of. Most of these pictures came right off the Hubble Heritage site because they published them. So anyway, there's a few other last observers here. So anyway, that's my story, and I'm sticking to it. Any questions, anybody?